our next example, we have f of x being this piecewise function. In the case where x is positive, the value of the function is 1, and when x is negative, the value is -1. So, in particular, the domain of this function is only defined for positive and negative numbers. It's not defined at 0. And you probably remember seeing something like this from calculus. And the only point at which the limit does not exist is at 0, and we're going to prove that. So the question you ask yourself if you want to know a limit exists, and this is a very informal because that's not being precisely mathematically defined, getting close to one number. Does the height of the function get close to one value as x goes to 0? And the answer is no, because it depends on which way you approach 0 from. If you're approaching it from the right, the height is a constant, +1. If you're approaching 0 from the left, the height is a constant, -1. All right, so I'll answer this question. Does the limit as x approaches 0 of f of x exist? No, it doesn't, and we'll show why now. So since we're showing that it does not exist, we're not going to start the proof off with let epsilon greater than 0 be given. I'm going to choose at one value of epsilon and show us where the rest of it fails. Now, before I do that, there's a little mathematical step I'm going to take in here without proving. It's very simple. As a matter of fact, it'd be a good thing for you to prove it. If the limit exists, I could draw the limit somewhere on the y-axis. You know, the function, if it were 0, I could draw the limit L right there. Or I could draw it up here. I could draw it anywhere. So my question is, maybe I'll make it a true or false. True or false? Most true or falses are false, but we'll see what happens here. Okay, every real number r is distance at least 1 away from 0 or 1. So true or false, every real number r, I guess I didn't even need to specify r since I didn't use it later in the sentence. Every real number is distance at least 1 away from 0 or 1. Is that true? Sorry, that's not true. Let me make it true. I intended it to be 1 or -1. Now, I'm telling you it is true. And it should be simple to, on a graph, if you draw the number r anywhere on this line, the very worst, the very extreme case is when r is right in the middle, r is equal to 0. And in that case, it's distance 1 away from both of the numbers. But if you move r up to here, getting it closer to 1, well, that makes it farther away from -1. And if you brought r down into the negative numbers, well, it gets it closer to -1, but this is an or. It is distance greater than 1 away from the number 1. Is there any question? Any question about that? All right. I'm just going to assume that we know that, and it is fairly obvious. Okay, so to show this, I'm going to say let epsilon equal 1. And you'll see that I chose 1 because of this 1 right here. Let epsilon equal 1. And what we're going to do, I'm going to put it in comments here, show that for every delta greater than 0, there exists an x in the domain where for every x that is very close to the limit L, that shouldn't be L, that should be 0. So for every x that is close to 0, within delta of it, and not exactly equal to it, to 0, we can find f of x minus L greater than or equal to epsilon, which is 1.
Do we put a symbol in between there exists and x?
I said it without writing it. There exists an x in the domain of the function. Normally for us, but not always, but normally the domain is always all real numbers, and so I will sometimes leave that off. No, but thanks for pointing that out. I was inconsistent from the previous ways I've done that. All right, let epsilon equal 1. Thus, 0, I'm going to define, actually let me do this before thus. I'm going to choose 2 points. Let's let x1 and y1 have values. x1 is going to have the value negative 1/2 of delta, and x2 is going to have positive delta over 2. And you can probably see why I'm doing this. That's negative delta, that's positive delta. If I pick a positive number, x, f of x is a 1. If I pick a negative number, f of x is a negative 1. Okay, so we've got x1, we've got x2, maybe I'll make that obvious here. So, f of x1 is the negative, so that's going to be a negative 1. F of x2 is positive, so it's going to be a positive 1. Thus we get the following. The hypothesis is satisfied in that they're going to be close to 0. Both of those hypotheses are satisfied, but either f of x1 minus the limit, which is equal to x1 is negative 1. Negative 1 minus the limit is greater than or equal to 1. Or, on the other side, f of x2 minus the limit, which this will be a positive 1, is greater than or equal to 1, which is epsilon. So we'll talk about it in a second. Let me just write the final line that says, therefore, the limit doesn't exist. F of x. I got lazy on the bottom. DNE just stands for does not exist. So to show that the limit doesn't exist, for epsilon equal to 1, now I couldn't have chosen anything bigger than 1, but I could have chosen any positive number smaller than 1 for epsilon. For epsilon 1, we needed to show that for every delta, and which we did, because we used delta to define our x1 and x2, whatever delta is, x1 and x2 are plus and minus delta over 2. So these two values are close to delta, but one of them has to be at least 1 greater than epsilon, as we talked about a little bit earlier. And if there's, just to make sure there's no question about what we did here. Here I replaced f of x1 with negative 1. So that's the distance between negative 1 and L. is at least 1. This one might look a little bit different. No, it doesn't. The distance between f of x2 and L is 1 minus L. So the distance between L and -1 and the distance between L and +1, one of them has to be at least 1.